Hi, welcome back to an introduction to formal logic. It's an open introduction. We're using an open source textbook. I guess I haven't really settled on the title yet because at the beginning of every video I call it something different. Why don't we call that a running joke instead of my lack of professionalism and lack of preparation for just decided to show up one day and narrate all my slides. So chapter 3 in For All X, a Lorain County remix, which you can download online, just Google For All X Lorain County, is going to be slowly introducing a formal logical system. Now, in the past 4 videos, I introduced a lot of the basic components and ideas of logic. Now, I've done these in a somewhat haphazard way because I wanted people to go into a formal system, at least the beginnings of a formal system, knowing what validity is, more or less, knowing what soundness was, what a statement was, that things could either be true or false, but not some other thing. Let me, should have erased the board before starting the next video. So, in a formal situation, what we're going to be doing is studying in an abstract way deductive logic. And deductive logic is concerned with truth-preserving inference in the most general sense. We can think about this in terms of a certain property, truth, being preserved across sets of specified logical operations. Now, the point of having formal tools, rather than the way we've been doing in the previous videos where we just kind of informally reason our way through, is that we can ensure that content neutrality is respected by systematically kind of replacing ambiguous language like if, then, or things arguments are about, like whales or mammals, with these well-defined elements like operators and variables, and a well-defined syntax. A syntax somewhat like a programming language, where what counts as a well-defined sentence or formula in a language is specified in advance exactly with no exceptions. So we're going to have rules for constructing sentences using specified well-defined elements. And using these together, we'll have our first system of formal logic. And in this system of formal logic, we'll be able to define all the things we've been talking about previously, like validity, invalidity, maybe not soundness. So why don't we just get started on that? And if you decide to start with this video, because in my introductory video I said that a good place to start might be chapter 3, if you want to skip over the kind of introductory part, then welcome aboard. All right, why are the slides changing? There we go. Okay, so formal logic is possible because we can separate the content of any specific argument from its logical form. And it's the logical form of an argument, not its content, that will determine validity, right? That the inference will preserve truth, right? Content neutrality means that it doesn't matter what the argument's about, the argument will be valid or invalid as a function of the structural relation between the premise and the conclusion. Or if you want to think about it a different way, that the information in the premises is implicit and the conclusion is only making some implicit information in the premises explicit. Which also means that for deduction, the truth of the premises guarantees the truth of the conclusion. That's the whole point. Now, in prior videos, I talked a little bit about Minesweeper. I introduced something called the MIU puzzle due to Douglas Hofstadter. Maybe you played around with the MIU puzzle. And these things have a kind of an internal logic to them too, right? There are rules, and I can make inferences on the basis of these rules, and if I do that right, I'll get deductively certain results. But the key difference here is that our formal logic is not just going to have a set of rules. It's all going to have meaning as well. It's not just a syntax. It's not just symbols arranged according to rules. It's also going to have a semantics, an interpretation outside of the system itself. It means something. It represents some aspect of, hopefully, reality. We're not just manipulating meaningless strings of symbols according to rules. Anybody could come up with an MIU puzzle, or happy face means frowny face. You can create rules of symbols that you can follow, but that doesn't mean it's logic. Logic is a kind of language, and it's a kind of language concerned with truth-preserving inference, that is, with correct reasoning, which means it has a semantics, it has an interpretation. It's not just symbol manipulation. So in this course, we're going to be discussing, in depth, 2 different systems of formal logic. First, sentential logic, and then quantified logic, which will build on sentential logic by adding new operations and new operators and new semantics on the existing structure of SL. Now, logic is logic, capital L, of course. But there are many systems that aim to capture what we mean by logic. Now, people often use logic in this homogeneous sense, that there's one correct logic, but there's many different systems that attempt to use logic and define it in a content-neutral form with a specific syntax, with specific rules. And these systems have been refined over centuries. So logic is logic, of course, but there's another sense in which there are logics, and that there are many different formal systems. And these formal systems are more or less expressive. They can do more or fewer things. So let's look first at Aristotle's logic and see what he did right, see what he got wrong. This is 2,500 years ago, but it was probably the most significant development in the history of logic. Why? Well, first of all, he might have just invented the notion of the variable. So, the variable is something we've already done in previous videos. We were taking English language arguments and putting them into content-neutral form. We were replacing specific elements of the argument with variables. We had an argument about recessions and falling dollar values, right? So recession was if recession, then, if R, then. So the R comes to represent the idea that of recession, but it could also be anything. If R, then it could be raining. It could be running. The variable replaces the content because we're interested in looking at the structural relations. In Aristotle's logic, this is the same thing. Aristotle was interested in the structural relations between elements of an argument. So he introduced the notion of a variable and also created an argument schema, which he hoped would capture all the forms of valid reasoning that there were. He didn't, but his attempt was really interesting. So this variable is an abstract element. It's capable of taking any of a set of predefined values. So for Aristotle, variables will represent a class of things. I'm going to do a little bit, my examples are not always going to be of classes. I'm going to refer to individuals, but just imagine that every reference to the individual is like a class defined solely in virtue of having contained that individual as a member. Don't worry about that. So variables represent classes of things, groups of things, collections, sets. We also have a membership relation, is. So a class could be a member of a different class. We have also quantifiers, all, some. And finally a negation, none. So if we combine variables, membership, quantifiers, and negations with a specific syntax, a specific form, will yield a restricted set of sentences that can be kind of systematically analyzed. So here's an example of an Aristotelian argument, a syllogism. Socrates is a person. All persons are mortal. Therefore, Socrates is mortal. So Socrates is inside the set of persons. All persons are inside the set of mortal things. Therefore, Socrates is inside the set of mortal things as well. That's a valid argument. For Aristotle, a sentence can either be universal, all X, S is P, a particular, some S or P, right? So, or affirmative or negative, right? Like no S or P. This yields actually four basic types of sentence. All X or Y, the affirmative universal. Some X's or Y, affirmative particular. No X's or Y's, negative universal. Some X or not Y, negative particular. These are the only types of sentences that can be constructed in Aristotle's logic. Now, for logic, it's always really important that you restrict the type of sentences that can be produced by having a well-defined syntax. Now, for Aristotle, there's only basically four types of sentences. Later on, when we do sentential logic, we're actually going to have a recursively defined syntax with infinitely many possible sentences. However, these sentences will always be created according to a set of specific rules. But I don't want to get ahead of myself. So an argument, for Aristotle, called a syllogism, always has two premises and a conclusion. And these are always going to relate three variables representing classes of things. So an Aristotelian syllogism will look like this. All A's are B's, all C's are A's, therefore all C's are B's. So to fill out the variables, I could say, for example, all people are mortal. All logic students are people. All logic students are mortal. Sorry, guys. So the three sentences of a syllogism could be of any 4 basic sentence types, yielding 64 syllogisms. But there are 3 variables, right? So we also need to account for the 4 unique different ways they could be arranged. So 64 syllogisms times 4 arrangements means 256 syllogisms total. Now, what's really interesting about Aristotle is that by restricting the arguments to this notion of sets of things, membership, quantifier, and negation, he yielded a restricted set of sentences. There's only 256 possible syllogisms. That's it. There's not an infinite amount. And he can actually, 256 isn't a lot. You can systematically write down every possible syllogism and see if it's valid or not. Then you can get an exhaustive list of all possible valid arguments, and logic is solved forever. Almost. So that's exactly what Aristotle did. He gave a list of all the valid syllogisms as a subset, as a restricted set of all possible ways you can arrange these kinds of statements together. There's 256 possible syllogisms. How many of them are valid? Only 24. For example, the following here is not a valid argument. No x's or y's. Some y's are z's, some x's are z's. Well, that's not a valid argument, right? No whales can fly. Some flying things are mammals, so some whales are mammals. So yes, some whales are mammals, but we can't get there on the basis of the premises. That wasn't the best example. Here's a valid Aristotelian syllogism. Some P's are M. All M are S. Therefore, some S are P. So, some mammals are whales. All whales are swimmers. Therefore, some swimmers are mammals. That's valid. So, the interesting thing about Aristotle, right, is that by creating, again, a restricted set of sentences, a restricted set of logical operators, and giving a distinct argument schema, we would be able to restrict and create a class, a set of sentences that we can then logically analyze to determine whether or not it's valid. And this was a really important insight, and in fact, for the better part of a couple thousand years, no one really improved on this logic. So, here's some penguins are black and white, some old TV shows are black and white, therefore some penguins are old TV shows. This is an invalid argument. This logic is a thing penguins aren't very good at. I was trying to find funny things in the slides with Google image search. Thanks, Glassbergen. Don't sue me. So, look, Aristotle's logic is 2,000 years old. It's obsolete, but, and we're going to talk about why soon, it introduced these really important conceptual innovations that are central to modern formal logic, right? The notion of the variable that can stand in for specified values, i.e. the whole idea of content neutrality. We specified the logical form of sentences and arguments. It had a specific syntax, a way of constructing the sentences. It restricted the sets of possible combinations of sentence types and variables, making it possible to systematically investigate the validity of the sentences involved. And this was really important, because prior to this, a lot of times we were evaluating arguments one by one, whether a specific argument about something was good or bad. When Aristotle wrote down his logic system, he abstracted away from specific arguments and was looking at validity in general. He was interested in which syllogisms were valid. All men are mortal. Socrates is a man, therefore Socrates is mortal. This is not just a good argument. It has a structure of a good argument such that no matter what we replace Socrates, mortal person with, it will still be a valid argument. This was the crucial insight that made Aristotle's system of formal logic the first true formal system. But it's also restricted. Using 3 variable syllogisms, using only quantifiers and only negation, doesn't do everything we want logic to do. It's only part of truth-preserving inference, part of how we reason. It's an artificial language. It's a simplified version of this more complex process, reasoning. It's a strength because you can be very systematic. You can figure out, given the elements of the logic, what kind of inferences are valid and which ones are invalid. There are 24 valid ones out of 256. That's tremendous progress. But it's difficult to represent something like an if-then argument. Either A or B. The kinds of reasonings we've already seen in the previous videos. It's really difficult to translate these in purely Aristotelian terms. Some of the arguments we've already looked at are basically impossible to translate. Worse still, there's all kinds of really logically intuitive relations, like transitivity, it's completely unclear how maybe a heroic effort to be able to do it. But like if I say A is taller than B, B is taller than C, therefore A is taller than C, there's no real way of representing that in a syllogism. So Aristotle's logic isn't good enough. So when I say something like Aristotle's logic is obsolete or fails to capture certain forms of inference, I'm not saying it's a bad logic. I'm saying it's incomplete. It does not formalize all truth-preserving forms of inference. So it's not that there's many logics and that logic is arbitrary and I can choose which logic I want depending on the circumstance. It's that any formal system has a limited amount of expressive power. Logic is logic, but tools that we use to talk about logic have their limitations. So any logical system is only as good as its formalism allows, and there's many different ones. Aristotle's is one such formalism. Sentential logic, which we're going to be looking at soon, is another. We can extend, lights went out of the room. Lights, thank you. Awkward. We can extend sentential logic into a more complex system. For example, quantified logic, which we're going to do later on in this course. Quantified logic can then be extended and supplemented also in various directions. We can do modal logic. We might want to do set theory. And these are all things, set theory is not exactly an extension of logic. That's not strictly correct. But, however, the point is there are many different logical formalisms depending on what we want to do. So the problem with Aristotle's logic that I'm trying to get at here is that it's limited in its expressive power. It could tell us a great deal about certain kinds of class memberships. It's a very good kind of Venn diagram logic. But it can't capture cause-effect arguments very well. Transitivity, some mathematical relations. So when we do sentential logic, we'll see that the vocabulary and the expressive power is larger in some ways than Aristotle. We're not going to be limited to the syllogistic form, for example. However, it doesn't deal with quantification at all. Quantified logic, which we're going to be doing later on, has all the virtues of SL plus the quantification properties of Aristotle. So it does more. However, the more expressive a formal language is, the more complex it becomes. It's harder to handle. But still, compared to a natural language like English, which is extremely rich and expressive, these are still better systems that we can use to investigate validity. So, the formal systems of logic that we're going to be studying are the basic foundations of what is called classical logic. Classical logic is the correct logic for truth-preserving forms of inferences. And it's very powerful, it's very understood, very well understood. Now, there are some assumptions baked into classical logic. And there are other logics that reject some of these assumptions that could be used under special circumstances. And it's actually a subject of tremendous philosophical debate. What is the relationship between different types of logic? And which logic might be the right one. Most people think classical logic is the right one, and that the other ones are not about truth in the right way. They're about something else. So some of you might be familiar with fuzzy logic in engineering. There's also three-valued logic where you have true, false, and something else, typically like indeterminate. There's computability logic, quantum logic, intuitionistic logic, which rejects the law of excluded middle, paraconsistent logic, which says there are true contradictions. And we can talk about all these different forms of logic later. So I know earlier I said logic is logic, and I still believe that. I still think classical logic is the logic of truth-preserving inference, and that when we modify the rules, we're actually in a way changing the subject, such that we're still doing the logic, we're doing the logic of something else. So the logic we're going to be doing in sentential logic and quantificational logic is going to be hopefully classical logic, not hopefully, it will be classical logic, that is, the logic of truth-preserving inference. So one of the foundational assumptions of classical logic is that statements are always either true or false. There's no third value. There's no in-between. There's no vagueness. This assumption is called bivalence. Sentential logic is bivalent in that both the variables and the operators are always either true or false. In the statement A and B, A can either be true or false, B can either be true or false, and it's the truth values of A and B themselves which will determine the truth value of the statement A and B. So let's just go over this again, because it's going to be a quite crucial component of what we're going to be doing here. So I have A and B. Bivalence means that A can be true or it can be false. B, bivalence means B can be true or it could be false. And crucially, the value of the whole statement, A and B, is going to be a function of the values here. A and B. If both A and B are true, then A and B is true, right? If I say it's raining and it's cold, if it's true that it's raining and it's true that it's cold, then A and B is raining and it's cold is itself true. So the truth value of the whole sentence is a function of the truth value here. Now there's more combination than true, true, false, false, of course, but if I say it's cold and it's raining and I look outside and it's sunny and warm, then false, false means my statement is false. So the value, it's either true or false, there's nothing else. And the value of sentences in logic are going to come from the value of its parts. It's going to be really important moving forward. Right? The truth values of parts of a sentence determine the truth value of the sentence as a whole. And we can represent any statement using a variable. Now, a statement is a sentence capable of being true or false. It's not a question or an order or an exclamation. And we're going to consider these as something about the world with a meaning independent of the language used to express that meaning. We can think about these as, the technical term is a proposition. So if I say grass is green, l'herbe est verte, Gras ist grün, right, German is terrible, right, I'm going to want to represent all these with the same variable because they're all true. So, consider the following two statements. I watch Game of Thrones. I can represent that with G. Now, G is a variable. It abstracts away in a sense from the content, but in my head I know that I'm using it to represent a sentence. Sentence 2, I watched Game of Thrones and Last Week Tonight. G for Game of Thrones and L for Last Week Tonight. Now, statement 1 here is what we're going to call an atomic sentence. It has no parts. Statement 2 is a complex statement. It's comprised of two substatements and the and joining them. So statement 1 is true if it's the case that I watch Game of Thrones. Statement 2 is true. Statement 2 is true if it's the case that I watch Game of Thrones and Last Week Tonight. So we have atomic statements, we have complex statements. Now there's special kinds of complex statements, and we're going to call these tautologies, and there's another kind called contradictions. These have a bit of a special status to them. Suppose I say either you watch Game of Thrones or you do not watch Game of Thrones. This kind of statement is called a tautology because it's going to always be true. Statements or sets of statements can also be contradictions. So we see G or not G is always true because of bivalence. If G or not G, suppose G is false. Suppose I do watch Game of Thrones, then either you watch or you don't is true. Now suppose I don't watch. Either I watch or I don't is still true. So no matter what is true because of bivalence, because things can only be either true or false. Likewise with contradictions, right, they're always going to be false. I watch and I don't watch Last Week Tonight. So both of these can't be true simultaneously, therefore it's a contradiction. Now tautologies and contradictions are actually going to play an important role in our formal system. So I just want you to remember for now, a tautology is a statement that's always true, a contradiction is a statement that's always false. Brienne of Tarth is the best warrior in Westeros. Brienne of Tarth is not the best warrior in Westeros. So the set of if I imagine sentences 3 and 4 as a set, the set itself is a contradiction because they can't all be true simultaneously. So we have atomic statements. We have complex statements, which are made out of different parts. Tautologies, which are always true. Contradictions, which are always false. We also have a notion of logical equivalence we should talk about. And all these features of sentences are going to be really important in our formal system, which is why I'm introducing them now. Translations of a statement to different languages should always be logically equivalent, because they mean the same thing. A pair of sentences such as, or within a language, if I say he's in front of the tree is behind him, both are going to be true, because they're saying the same thing. Statements are logically equivalent when they must have the same truth value. If one is false, the other must be false. If one is true, the other is true, is also. Atomic sentences can be equivalent. Complex sentences can be equivalent. For instance, A and B is equivalent to B and A. It's saying the same thing. A set of sentences is logically consistent if all the sentences in that set could be true at the same time. So I have an odd number of coins in my pocket. I have money in my pocket. There's a pink elephant in the classroom, and Jon Snow knows nothing. These things could be true. There could be a pink elephant. There isn't, but there could be. In the sense that this is very weak conditions. A set of sentences is consistent roughly if they don't contradict each other. So consistency, equivalence, contradiction, tautologies, these are going to be kind of the important features of sentences and sets of sentences as we move forward. Formal accounts of these properties are going to prove really quite critical to having and understanding the features of our logical systems, finding out whether an argument is valid or not, finding out the properties of formal sentences. So as we move forward and we have a formal system to test the validity of arguments and find out the properties of sentences, all these are going to be quite crucial. Okay, last thing in this video here. Validity, of course, is the most important concept that we have here. And the idea behind validity is that it's impossible for a valid argument to have true premises and a false conclusion. Or the truth of the premises guarantees the truth of the conclusion. Now, there are special cases of validity. An argument with a tautology as a conclusion is always valid. An argument with a contradiction in the premises is always valid. That's weird, right? So why? Explain these two special cases with references to the definition of validity. And second exercise, provide an example of a valid but unsound argument and of an invalid but sound argument. Now, these two exercises are conceptual ones to make sure we really understand two things: the concepts involved in the class and the kind of reasoning involved in the class. So, again, an argument with a tautology as a conclusion is always valid. An argument with a contradiction in the premises is always valid. What is validity? That it's impossible to have true premises and a false conclusion. Okay, pause the video, work on those. Did you pause? Pause. Okay, let's work on these answers. An argument is not valid if and only if two conditions can be met. First, the premises are true. Second, the conclusion is false. All right, so we have to have true premises and a false conclusion in order for the argument to be invalid. So if I argue that clam-flavored ice cream is delicious, which it is, triangles do not exist, therefore 2 plus 2 is 4. So why is this argument valid? Well, the conditions for invalidity simply can't be met. It's impossible to have true premises and a false conclusion. Why? Because the conclusion can't be false. 2 plus 2 is 4 can't be false. You can't have true premises and a false conclusion. Another way of doing it might be, for example, right, I keep the same premises: clam-flavored ice cream is delicious, triangles don't exist, therefore either I watch Game of Thrones or I don't. Either I watch Game of Thrones or I don't is a tautology. So I can't have true premises and a false conclusion if my conclusion is a tautology, because my conclusion can't ever be false. Now, this is a weird case of validity, and the reason I'm talking about it, it's actually not going to be that important in the grand scheme of logic. It kind of illustrates an abstract point about the kind of reasoning we're going to be engaged in logic. You really have to take the letter of the law. You might think, it doesn't make a lot of sense to have a valid argument with a tautological conclusion because that's not what logic is about, or that's not. Just stop all that kind of reasoning and just look at the letter of the law in terms of the definition of validity. It's impossible to have true premises and a false conclusion. It's impossible to have true premises and a false conclusion if the conclusion is a tautology, so it satisfies the definition. That's all you ever need to think about. And one of the reasons I'm bringing this up now is, again, to kind of prime your brain to be able to work in these specific ways. So an argument with a tautology as a conclusion is always valid. You cannot have true premises and a false conclusion when the conclusion is necessarily true. Same goes for something like this. Bagpipes sound good. Bagpipes do not sound good. Scottish people are deaf. Now, premise 1 and premise 2 contradict each other. So it's not possible for the premises to be true. So you can't have true premises and a false conclusion. You can't have true premises and a false conclusion if the premises can't be true. So what we have is, again, is a technically valid argument. Why? Because the premises are contradictory. So you can't meet the conditions for invalidity. You can't have true premises and a false conclusion because the premises can't be true. Again, when it comes to logical reasoning, we're going to have to abstract away from everything else we think we know about the nature of logic, of meaning it, and really focus in on the definitions and the consequences of those definitions and nothing else. Okay, we're going to end here. I promise you in the next video, we are absolutely going to start introducing sentential logic as a formal system. Thanks for watching.